in the previous unit, we explained the classical propositional logic with its language, semantics, logical consequence, and all that. Now, in this section, we are gonna problematize this logic, right? And we are gonna consider the first paradox we are gonna discuss in this course, which is the sorites paradox, and the problem of vagueness broadly considered, right? Now let's go for the sorites paradox. Suppose that we've got a series of objects, of patches of color. The first is clearly red, right? The last one is clearly yellow, and so clearly not red. But the funny thing is that for any object in the series, this object is extremely, extremely similar to its neighbors, so that you cannot discriminate them in color by the naked eye, right? So consider the situation, right? This is a very long series, and this one is clearly red. This one cannot be discriminated from this one. So it seems that all these conditionals, right? If the first one, if this one is red, then the next one is red. All these series of conditionals seem to be true, right? Because they are so similar in color, right? Now the problem comes in classical logic with the fact that modus ponens, this pattern of inference, is classically valid, right? And so it follows from the fact that the first guy is red, and the validity of this rule that if all these conditionals are true, then the last guy is red as well, right? In other words, it follows in classical logic that if this guy here is red and this other one is not red, then there is a false conditional, right? So there is a conditional that is false. Now this is striking. This is truly remarkable because this means that there is one item that is red followed by some other item that is not red, right? But how can you, I mean, if they are so similar in color, it seems that this is an impossible situation. And further, how can we just prove based on logic that meanings have such extremely subtle, can make these extremely subtle distinctions, right? So this is very puzzling. This is very puzzling. This is the sorites paradox, right? Now the second thing I would like you to consider is something related to what it is called borderline cases, right? So take the example of Tim, right? This is like a classical example in the literature. So Tim Williamson is thin. Well, Tim Williamson is clearly thin, right? But I don't know why he puts the example. So Tim Williamson is thin. So Tim is supposed to be like a borderline case of for the predicate thin, right? So that some people is clearly thin, some people is clearly not thin, right? But Tim is somehow in the border, right? So we cannot decide simply, you know, we might know all the relevant facts about Tim measures. We might know everything we should know, seemingly, about the meaning of the predicate because we are competent speakers. But still, it is somehow unclear whether Tim is thin, right? Because Tim lies somehow on the border, right? So that's intuitively a borderline case. Now, it is supposed to be part of the phenomenology of borderline cases that competent speakers won't just accept, you know, for example, that Tim is thin and reject that Tim is not thin, right? So in borderline cases, competent speakers tend to hesitate between acceptance and rejection, right? So there is a sort of symmetry. There is a sort of symmetry in the dispositions, right, in borderline cases between acceptance and rejection. Now, classical logic, classical semantics in particular, tells you that either Tim is thin is true or Tim is thin is false, right? So classical semantics forces you to introduce an asymmetry where seemingly our use of the predicates is known, right? And this seems utterly impossible if meaning is determined by use, right? Okay, so these two problems seem to put into question the classical logic and semantics, right? Now I'm going to leave you with a very nice example of a sorites paradox. I don't know if you have seen Noah Kalina's everyday video. This is a very nice example of a sorites paradox in video form. So Noah starts to take pictures of himself when he was in his early 20s. And the question is whether you can identify a point in the video where Noah is in his early 20s, and a second later he's not in his early 20s. So that's the sorites paradox. In the previous video, we explained how vagueness somehow seems to question the classical logic and semantics, right? So in this video, we are going to introduce two logics, right, which are some sort of generalization of classical logic, K3 and LP. Now, as we did before, in order to specify a logical consequence, we need to set a language and a semantics, right? And the language for K3 and LP is going to be the same as the classical propositional language, right? We've got a vocabulary in which we distinguish the non-logical vocabulary with propositions, propositional variables, and a logical vocabulary with constants, right? So conjunction, disjunction, negation, conditional, and the parentheses. So the language is just the same. Now all the action is in the semantics, right? In particular, in classical logic and interpretation of the non-logical vocabulary was an assignment of truth values, true and false, to each propositional variable. Now in this case, an interpretation is going to be a function from propositional variables to three truth values, right? So it's a very modest modification of classical semantics. So instead of having two truth values, we're going to have a middle value, right? And all the game is going to be related to this middle value, right? Now once we define an interpretation as a function going from the propositional variables to truth values, not to two but to three truth values, right? Now we have to define how this interpretation extends to all the formulas of the language, right? And the extension of the interpretation that we are going to use, you've got room for different options here, right? But the one we are going to use, it is called strong Kleene schema, right? Which assigns to a conjunction the interpretation of a conjunction gives you the minimum of the truth value of its conjunct, right? So this means that if A takes value 0, then the interpretation of A conjunction B is going down to the value 0, right? And if A takes value 1, say, but B takes the middle value, then the interpretation drops to the middle value. So always takes the minimum value between A and B, right? And the interpretation of negation, right, equals 1 minus the interpretation of A, right? So this might look a bit strange, but the idea is very simple. So negation will map 1 onto 0, 0 onto 1, and maps the middle value onto itself, right? So negation flips the value when you are considering 1 and zeros, right? But when negation takes the middle value, it returns the middle value, right? Now I would like you to notice that, in fact, this can be left as an exercise, but in fact, these interpretations are generalization of classical interpretations, right? In the sense that for the classical values, if A and B take only classical values, if A and B take only 1s and 0s, then this conjunction behaves completely classical, right? This is a relevant fact that we will use later. Okay, so far so good. Nothing very fancy, right? So we've got the language is the same, interpretations are slight modifications, right, in which we have an extra middle value, and we adapt the extension of the interpretation to accordingly, right? Now we reach a critical point in this discussion, right, which is how do we have to interpret the middle value, right? Because we've got more than one option, right? It is clear that taking value 1 means being true, right? Taking value 0 means being false, but what does it mean to take the middle value, right? Well, we've got at least two options, right? We can say that the middle value is like a way of being true, right? But if the middle value is a way of being true, given the meaning of negation, right, that the middle value maps onto itself, a sentence and its negation might both be true, right? This is called, or we call it, tolerant truth, right? So we will say that a formula A is tolerantly true in an interpretation just in case it takes value more than 0, right? So as you can see in this explanation, the tolerant truth allows for like an overlap, right, between truth and falsity. Now we can take the middle value as a way of being untrue, right? This is strict truth. So strict truth, we can define a formula A is strictly true in an interpretation just in case A takes value 1, right? If we interpret truth in that way, then the middle value is a gap, right, between truth and falsity, right? And this makes a huge difference when we go to logical consequence, right? Because generally speaking, logical consequence, when people define logical consequence, they are thinking that, well, logical consequence should preserve a notion of truth, right? If we interpret that the middle value is a way of being true, then logical consequence should define, or this motivates the definition of logical consequence as LP, right? In which what it is preserved is tolerant truth, right? In the sense that delta is an LP consequence of gamma, just in case there is no interpretation, where all premises take value more than 0, so all premises are tolerantly true, and all conclusions take value 0, so no conclusion is tolerated, right? That's LP. The second option is taking as your favorite notion of truth, strict truth, right? And define your logical consequence accordingly, right? This is K3. Delta is a K3 consequence of gamma, just in case there is no interpretation where all the gammas take value 1, all the gammas are strictly true, and all the deltas take value less than 1. All the deltas are less than strictly true, right? Now, K3 and LP are different logics, right? So consider just that K3 preserves strict truth, and strict truth leaves a gap, right, between A being strictly true and A being strictly false, so it leaves a gap between truth and falsity, while LP leaves a glut, so to speak, right, an overlap between truth and falsity. And actually this is reflected in the logic, right? So K3 is paracomplete in the sense that this principle, which was classically valid, is no longer valid in K3, right? And this behavior of the logic matches with the intuitive reading of the middle value, right? Like leaving a gap between truth and falsity. And LP is paraconsistent in the sense that this principle fails, right? A conjunction, not P, was classically unsatisfiable, but in the case of LP, it is satisfiable, right? Actually, this is called a failure of the principle of explosion. I leave you a very interesting story about this principle. You should take it seriously. We have introduced our new logics, K3 and LP, and now we are going to present some facts and the relations between these logics and classical logic to get a feeling of what's going on with this, right? Okay, so I'm going to present in the first place some facts. Then we are going to explain a concept that is a central concept in this course, which is the concept of duality. And then we will see the relations between K3, LP, and classical logic. Okay, so let's go for the facts. Fact 1. Delta is implied in LP by gamma just in case the inference holds in classical logic, right? This fact means that any inference that is valid in LP is classically valid, right? And this fact can be easily proved if you notice that any LP interpretation is a classical interpretation, right? So that in the contrapositive form, this would say something like, if delta is not a classical inference, if delta is not a consequence of gamma in classical logic, then delta is not an LP consequence of gamma, right? These two statements are equivalent. Of course, if you've got a classical model in which every member of gamma takes value 1 and every member of delta takes value 0, since LP models are a generalization of classical models, as we pointed out in the previous video, then you've got a model in which all the gammas are tolerated, take value more than 0, and all the deltas take value equal to 0, right? So this is the first fact, that any LP valid inference is classically valid. The second fact, if a formula is classically valid, then for any 3-valued interpretation, that formula takes always value more than 0, right? So here the idea is that if you've got a formula that is classically valid, when you jump to 3 valid interpretations, then the value of the formula can drop to the middle value, but never to 0, right? So that's an interesting point, right? If something is classically valid, when you jump to 3 valid interpretations, the value can drop to the middle value, but never to 0, right? Okay, and the third fact states just something relatively trivial, that any formula in this language can take the middle value, right? With these 3 facts and the notion of duality that we're going to explain, we will be able to set all the relations between the 3 logics. So let's go for duality. Okay, so a notion of logical consequence intends to, so usually it is defined as preservation of some notion of truth, right? So generally speaking, when we define logical consequence from gamma to delta, we intend to capture the idea that for some notion of truth, if all the gammas are true, then some of the deltas is true, right? Now consider this statement, but in contrapositive form, right? This statement in contrapositive form says, if all the deltas are untrue, some of the gammas are untrue, right? You should retain this in your mind. Now consider this. This is the contrapositive inference of this inference, right? So this inference, given that not A is true, means that A is false, right? This inference means if all the deltas are false, some of the gammas are false, right? Now what's the point? The point is, do these principles, do these inferences express the same fact? This one say, you can translate it to, if all the deltas are untrue, some of the gammas is untrue. This one says, if all the deltas are false, some of the gammas are false. Do they coincide? Do they express the same content? Well, it depends on whether untruth and falsity are the same, right? If untruth and falsity is the same thing, then of course this holds immediately. And of course classically, and being untrue and being false is the same thing, right? So in particular, classical logic, as we will say, classical logic is self-dual, right? Because being untrue and being false is the same thing. Now when we move to K3 or LP, you can easily see that being untrue in K3 and being false are different things, right? And the same goes for LP. So actually, this inference does not work for either choice of K3 and LP. So if you put here K3, if you put here K3, this is false, right? So K3 is not self-dual. However, and this is something you should try, like reading the notes and working yourself. You should take like acquaintance affinity with this idea. K3 and LP are each other's dual, right? So there we go. So the duality in the case of K3 and LP does not hold between K3 and itself or LP and itself, but between K3 and LP, right? Now with this in our hands, we can state the relations between classical logic, LP, and K3. So let's do it. Okay, so we've got classical logic. We know that any LP valid inference is classically valid, right? And our first question is whether it is also the case that every classically valid inference is LP valid. And the answer is no. Why? Because in particular, as we pointed out before, this inference is not LP valid, right? Why? Because being LP unsatisfiable means taking 0 in every interpretation. And in LP interpretations, this is fact 3. This is fact 3. Any sentence can take the middle value, right? And relying on this fact 3, we can further show that actually every set is LP satisfiable, right? For the simple reason that you can assign the middle value to all the sentences in that set, right? So there are no unsatisfiable sets in LP, right? Or in other words, if you want, LP is empty on the right, right? Of course, classical logic is not empty on the right. Now, so any LP valid inference is classically valid. There are classically valid inferences that are not LP valid. Let's go for another fact. Relying on fact 2, we can show that although LP is empty on the, sorry, I said on the right. It should be on the left, right? So LP is empty on the left, right? Although LP is empty on the left, it is classical on the right. Why? Because being LP valid means not taking value 0, right? So suppose that you've got a classically valid sentence. Well, this sentence, in 3 valid interpretations, its truth value can drop to the middle value, but never to 0, right? So it will be true, tolerantly true, or true by LP standards in any interpretation, right? So coming back to this picture, although LP is empty on the right, on the left, LP is classical on the right. So a set is LP valid if and only if it is classically valid, right? Right. So now, relying on duality, we can end up constructing these relations that I left to you to consider these very clever truths I'm going to tell you. So K3 is also strictly weaker than classical logic, and actually K3 is classical on the left, right? But K3 is empty on the right. Oh. Right? So just to summarize, to recap, we've got some facts, we've got duality, right? And relying on these facts, we can relatively easily show that LP and K3 are both weaker than classical logic, that LP is classical on the right, but is empty on the left, and the dual situation for K3, right? So K3 is classical on the left and empty on the right, okay? In the next video, we will see how the weakness of these logics help us to solve the sorites paradox, not in the next video, but in 2 videos. We have explained K3 and LP for the classical propositional language. We showed or tried to show the relations between these logics. And now we are going to show how to extend the tableau method to check for logical consequence, right? This is going to be very useful to, if you want to check for a particular inference whether it holds, you can use this method, right? Now recall that the method of tableaux was rules to construct a tree to show satisfiability, right? So in particular, we could translate any question about logical consequence into a question about satisfiability, right? So if we wanted to check whether delta is a logical consequence of gamma, we should ask to our tableaus whether the set containing the gammas plus the negation of the deltas is or is not satisfiable, right? So that was our strategy. Now consider what happens in this case. So recall that LP is empty on the left, right? So in general, this same pattern won't reproduce here, right? So we won't have this equivalence. Right? This strategy won't work. And what we are going to do is a very simple modification of the tableau system, introducing tags, introducing like labels to indicate whether we are going to check for strict satisfiability or tolerant satisfiability, right? Why is this so? Well, because if you reflect on the definition of logical consequence for LP, for example, the definition says there is no interpretation where all the gammas are tolerantly true and none of the deltas is tolerantly true, right? But come with me. Not being tolerantly true does not equal to the negation being tolerantly true. Not being tolerantly true equals to not A's being strictly true, right? So we need to mark the differences in our tableau to know whether we are checking for tolerant truth or for strict truth. And in particular, the equivalence that does hold is delta is an LP consequence of gamma, just in case there is no interpretation where all the gammas are tolerated and the negation of the deltas are strict, right? So that's the relevant point. So delta is an LP consequence of gamma, just in case there is no interpretation where all the gammas are tolerantly true and the negation of the deltas are strict, right? Which is another way of saying the deltas are not tolerated, right? And something similar happens in the case of K3. Delta is a K3 consequence of gamma, just in case there is no interpretation where all the gammas are strict, right? So you can see the change in the tag, in the label, and the negation of the deltas is tolerated, right? So you've got the dual situation, right? Now, what are the rules like for our tableaus? The rules for our tableaus are exactly the same as in the classical case, with the unique exception that we are going to use a tag, right? So we are with each formula in the tree, we are going to introduce a tag saying whether we are checking for strict or tolerant satisfaction, right? And the only thing that we have to do is to carry along the tag, right? So for example, if we've got that A conjunction B is strict, well, that will be the case only if A is strict and B is strict, right? Or suppose that we are checking whether the negation of a conjunction is tolerated, where the rule is exactly the same as in the classical case, with the unique exception that we carry the tag along. And the whole trick is not so much in the tags, but the whole trick is in the conditions for a branch to close, right? So what are the conditions for closing a branch? Suppose you've got a formula and its negation, right? Suppose we've got a formula and its negation in a branch, but we are checking for tolerant satisfaction. Then this branch does not close, right? Because if A takes the middle value, then A and not A are both tolerated, right? So this is not enough to close a branch, right? Now, if we have something like this, that A is strict and not A is tolerated, then that's enough to close a branch, right? Just reflect on the graphic, right? If we've got that not A is tolerated, then not A should be here, but that A is strict means that A is here, right? So these two conditions cannot be fulfilled at the same time, right? So a branch will close when we've got either strict or strict and tolerant, but not if we have tolerant and tolerant, right? Let's see an example. So we question whether this inference holds, right? This inference is modus ponens in inference form, right? So it's an interesting inference. Okay, so we just list the premises and negate the conclusion. And since we are asking about LP, we put the tag T on the premises and the tag strict on the conclusion, right? We've got this formula cannot be analyzed, this other formula cannot be analyzed, we've got to analyze this one, okay? And the analysis tells us not P tolerated and Q tolerated, right? So we've got these two branches and the tree is finished, right? Now we've got not Q strict, Q tolerated. This is enough to close this branch. But here we've got not P tolerated and P tolerated. But that's perfectly fine. That's fine. Why? Because we can find a model in which not P takes the middle value, right? So both P and not P are tolerated. Q should take value 0, right? Because not Q is strict. And that will be a model to show that modus ponens is not LP valid, right? We will make use of this in a moment. Excellent. We had good fun so far. We learned lots of things about K3, LP, but it's time now to see how these logics can help us to solve the sorites paradox, right? So let's look again to the sorites series, right? Just to remind you, this first element of the series is red, is clearly red. The last element is clearly not red, right? But each element in the series is very similar to its neighbor, right? So it seems that all the conditionals telling you that if this one is red, the next one is red, all these conditionals look to be true, right? Because otherwise it seems that we are making a very subtle distinction between elements that are very similar in color, right? So the problem in classical logic was that although if the first is red and the last one is not red, then there must be a false conditional, right? In particular, because the inference of modus ponens, this inference here, this inference is classically valid, right? So since the inference that leads you from the first one being red to the last one being red is valid, there must be a false conditional with a true antecedent and a false consequent, right? Sharp distinction. Okay, so when we go back to K3 and LP, these logics are going to help us to explain what's going on in the sorites series, but they will give us very different results, right? In the first place, let's concentrate on the semantics. So a conditional, A conditional B, is the material conditional is equivalent to the disjunction of the negation of the antecedent and the consequent, right? And this is going to have the value of the maximum between the negation of the antecedent and the consequent, right? So if we go to the sorites sequence and we concentrate on these conditionals, A1 is read, then A2 is read, AK is read, then AK plus 1 is read, etc. What we see is that each conditional is, at the beginning, each of these conditional takes value 1, right? At some point, the truth value of the conditional drops to the middle value, right? But at some point, again, the conditional goes up, right? Because at the beginning, the antecedent, this one is read to degree 1, right? So its negation takes value 0, right? But this one is, we can suppose, read to degree 1, right? So it takes value, the maximum value, right? At some point, this one might be read to degree 1, and this one to degree half, right? So the negation of this takes value 0, but still this one takes value half, right? And the disjunction will take the maximum. So the idea is that the value of the conditionals never drop to 0, right? Okay, so we've got two different solutions in K3 and in the case of LP. In the case of K3, modus ponens, as you can check now that you know how to use the tableaux with this kind of logics, modus ponens is K3 valid, right? So this inference here is valid in K3, right? So actually, what someone holding this logic would say about this paradox is that the reasoning, the inferences used in the paradox, the reasoning is valid. But the argument is unsound, right? Although the reasoning is valid, some premise is not true, right? So that's the K3 solution. And you can say, well, we've got the same problem that we have in classical logic, right? And the guy holding this solution will tell you no, because in classical logic, being untrue means being false, right? And this means that there is a sharp transition from falsity, from truth to falsity, right? In the case of K3, although some premise is untrue, the conditionals are never false, right? And this guarantees that there is no conditional with true antecedent and false consequent, right? So, I mean, of course, there's a lot of discussion going on here, but someone holding K3 might still want to say that there is no sharp transition from truth to falsity, right? Okay, the second solution is the LP solution, right? So in this case, for LP standards, if you remember, for LP, being true means taking value more than 0, right? So for LP standards, all these conditionals are actually true, right? What happens in the case of LP is that although all the premises are true, the reasoning in the paradox is not valid. If you remember in the previous video where we put the example of a tableau for LP, we showed that this inference here does not preserve tolerant truth, right? So for K3 standards, the reasoning, the premises are true, but the reasoning is not valid. Okay, so which solution is better, right? Now, which solution should we stick to? So should we hold K3? Should we hold that some premise is less than true, although not false? Should we hold LP? So should we hold that all the premises are true, but the reasoning is not valid? It is not easy to say, right? But I would say that in a sense, the LP solution is better, right? Why? Because the LP solution tells you that the premises are true, and from a psychological point of view, the truth of these conditionals is so plausible that I think that this sort of solution, in a sense, is better than K3 solution. Of course, the problem of LP is that modus ponens is not valid, right? So although these conditionals are true, in a sense, these conditionals are too fragile, right? And they cannot express tolerance like in a robust way. Okay, so in the next video, we are going to see a different sort of solution with some striking consequences, making use of these three truth values. See you then in a minute. So this is the last video, and I prepared something special for you. We are going to discuss a very new solution to the sorites proposed by some very smart young philosophers, David Ripley, Paul Ligre, Robert van Rooij, and I myself. And the motivation for this solution comes from this sort of puzzling situation with LP and K3, right? So we said that we explained how classical logic is self-dual, right? LP and K3 are each other's dual, right? And so any inference that is valid here in contraposed form and the other way, right? So in the end, some authors have suggested that the benefits and the shortcomings of each logic are like represented in the other in dual form, right? So we've got this sort of very symmetric situation. Okay, so reflecting on the notions of truth involved in LP and K3, we can try to recover self-duality, right? In particular, we've got that another name for LP will be TT, right? Because LP is preservation of tolerant truth, in the sense that an inference is LP valid just in case there is no interpretation where all the premises are tolerated and no conclusion is tolerated, right? So LP valid inferences drive you from tolerated premises to tolerated conclusions. The same goes for K3, but with strict truth. So K3 drives you from strictly true premises to strictly true conclusions. Okay. Now we can recover duality in the following way. So forget about logical consequence as preservation of truth, of some form of truth, and think on logical consequence as absence of a counterexample, right? Now this idea might liberalize a bit your mind, and you can think, hey, let's forget about just a single notion of truth. Perhaps logical consequence can involve more than one notion of truth, right? And in particular, we can recover self-duality if we mixed these two notions of satisfaction, tolerant truth and strict truth, right? So let's say that delta is an ST consequence of gamma, just in case if all the premises are strict, right? If all the gammas are strict, take value 1, then some of the deltas are strict, right? Or there is no interpretation where all the gammas take value 1 and all the deltas value 0, right? So this notion of logical consequence drives you from strictly true premises to tolerated conclusions, right? And some striking feature of this notion of logical consequence is that it's actually an alternative definition of classical logic, but over 3 valid semantics, right? There are different ways in which you can see this, right? But one easy way is looking at the tableaux, right? Recall that for ST, right, for ST, the tableaux should work like this. If you want to check this, you should write the gammas, check the gammas for strict satisfaction, and the negation of the deltas for strict satisfaction as well, right? And of course, the three rules are classical rules, right? So if any of these trees closes in classical logic, they will close if you've got that everything is being checked for strict satisfaction, right? So this is an alternative definition for classical logic. Now you might be wondering what good is in this solution if we have classical logic, right? So that there were problems with classical logic. Well, actually, ST is classical logic for the classical vocabulary, right? But very often, talking about paradoxes requires talking about something more than just logical vocabulary. And in particular, though we didn't discuss first order semantics for K3 or LP, I'm gonna make this slide tweak here. We could expand our language with similarity relations, right? So these similarity relations will record, for example, in sorites series, that two objects are very similar, are very close together, right? And one way to give the semantics for these similarity relations is saying that A and B are very similar in relation to a predicate P, whatever, just in case the absolute difference of the sentence A is P and P is B is less than 1. In other words, just in case whether A is P and B is P are close in truth value, right? So it is not the case that A is P takes value 1 and B is P takes value 0, right? So in that case, we can say that these two objects are similar. With this very small introduction into the logic, we have these very nifty results, these very nice results. First, the tolerance principle for any x and y, if x is P and x is similar to y, then y is P, that's actually ST valid, right? So this principle is valid in ST. This way we address what in a previous video I call the psychological question. So we explain why vague predicates seem to be tolerant. Well, because they are tolerant, right? So you can use this principle in your inferences, right? Another nice point, modus ponens, unlike in the case of LP, right? LP could hold that all the conditionals in the sorites series are true, right? But modus ponens failed in LP. Now, modus ponens is ST valid, right? Why? Because ST augmented with these similarity relations is an extension of classical logic. So any inference that was classically valid will be valid in this new logic. Third point, ST is not transitive, right? That's the trick, like to block the sorites paradox. What fails in ST is transitivity, also known the cut rule for proof systems, right? So you might have that A entails B in ST, B entails C, but it might be that A does not entail C, right? So in a sense, this is very, like, in a sense, it's very nice if you look at like the phenomenology of a sorites series, right? Because it seems that in the case of sorites series, you can say, well, okay, so if the first is red, the following must be red, right? Okay, if this one is red, another one is red. And you can make like single steps along the sorites series. But when you try to put all the steps together, then that's the point where things go wrong, right? So this very nice solution, there are a couple of papers on this, which I invite you to read. Even if you want, you can email me and I will send it to you.